In the second part of section 9.1, we are going to look at the properties of limits and finding limits algebraically. First, in looking at the properties of limits, we have a little bit of setup for the properties. We have two functions, one function named f and one function named g. And we are going to assume that the limit as x approaches c, just some number, of the function named f of x has a value of L. And the limit as x approaches the same number c for the function named g of x has a value of m. Then our first property says that the limit as x approaches c of k equals k. K stands for a constant. When you are writing limit, remember that you either put the name right after the LIM or you put the actual function after the LIM. In this example, we have just the function, which is k, any constant. So that is saying the same thing as if we had something like the limit as x approaches, let's just say 2, of the function that is 4. So what does that mean? That means that our function that we are talking about is y equals 4. Well, what is the graph of y equals 4? If you think about that, the graph of y equals 4 is a horizontal line through 4. And when we are finding limits, the limit, the short and sweet definition of a limit is the limit is a y value. So what this problem of the limit as x approaches 2 of the function 4 is saying is as you get closer and closer to the x value of 2, what y value are you approaching? Well, if we are talking about a horizontal line, the y value is always 4. So this limit would be 4. The short and sweet idea for this property is that the limit of a constant is the constant. So if I were to ask you something like the limit as x approaches -5 of 1, that answer will be 1. If I ask you something like the limit as x approaches 50 of 3, that answer is 3. If what you have right after LIM is just a constant, that answer will always be the constant because that function is always a horizontal line. Our second property of limits is that if x is approaching c and your function is x, that answer will just be c. In this case, the function is y equals x. Well, if you think about the function y equals x, y equals x is the 45-degree line that runs through quadrants 1 and quadrant 3. And on that line, if x is 0, y is 0. If x is 3, then y is 3. If x is negative 10, y is negative 10. So if we wanted to, on this function to find the limit as x approaches 4 of that function, well, think about if x is 4 on this line and you go up here, y is also 4. So that equals 4. If we were going to do the limit as x approaches negative 2 of the function x, well, if x is negative 2, then y is negative 2. You've come down to negative 2. So that answer is negative 2. So if you ever want to find a limit of the function x, whatever number you're approaching, c, you're just going to plug that in for x. On property 3, we are told that the limit as x approaches c of the function f of x plus or minus the function g of x is equal to the limit as x approaches c of the function f of x plus or minus the limit as x approaches c for g of x. So let's say, for example, that we have something like the limit as x approaches 2 of the function x plus 5. What this property is saying is that we could rewrite this as the limit as x approaches 2 of the function x plus the limit as x approaches 2 of the function 5. Well, we just learned from properties 1 and 2 that if your function is just x, you substitute the number in, so you would have 2 plus, on property 1, we learned that the limit of a constant is the constant, so that would be 5, and then our final answer would be 7. In looking back at the work that we just did, writing out this first step was kind of tedious. So if you think about, if we go back to our original problem of the limit as x approaches 2 of the function x plus 5, if we had just put the 2 in where the x is, we would have gotten the same answer. So we are going to skip writing out this big long step and just substitute the 2 in for x. But one of the things that I want you to notice is that once you start substituting the number in, you stop writing LIM on the front. Limit property 4 is very similar to limit property 3, except for the operation changes to be multiplication. So for example, what if I had the problem of the limit as x approaches negative 1 of the function 5x? What this property is telling me is that I can split this into the limit as x approaches negative 1 of 5 times the limit as x approaches negative 1 of x. But as we learned on property 1, the limit of a constant is the constant, so our first answer would just be 5. And on property 2, we learned that we just need to put in the number for x, so we would get -1, which gives us -5. So as on property 3, this step is a lot of wasted time. What we can do instead is, if we have something like the limit as x approaches 4 of 12x, we just substitute the 4 in for that and make it 12 times 4, which is 48. If we have something like the limit as x approaches 3 of x squared, what you need to realize is that that's the same as if we just had the limit as x approaches 3 of x times x. So we would rewrite that as 3 times 3. Remember, once I start putting the number in, I stop writing LIM on the front, which gives us 9. The basic idea on these remaining properties is that you should just substitute whatever number you are approaching in for the x, and that number is your answer. All of these properties that we talked about lead us to one basic rule we can use for polynomial functions. The limit as x approaches c of f of x, where f of x is any kind of polynomial function, is the same as f of c. And if you think back to your algebra days, f of c means plug c in for x in the function. So to practice this concept, we are going to look at these two examples of finding the limits. And if you look inside the parentheses, this is a polynomial function. So all we need to do is substitute what number we are approaching where the x's are. So on A, because we are approaching 4, it will be 4 squared minus 4 times 4 plus 3. So we get 16 minus 16 plus 3, so our final answer is 3. On the second one, we have a polynomial function. We are approaching -2, so we will have -2 that we are cubing minus -2 that we are squaring plus -2. -2 to the third. When you are putting these in on your calculator, you need to put a negative number in a set of parentheses, or you will not always get the right answers. -2 to the third is -8 minus -2 squared is +4, and plus a -2 could be written as -2 or just -2. And if we do that calculation, we get -14. So limits for polynomials are not bad. You just substitute the number for x. One of the very common problems that they do in the limits part of calculus is ask you to find limits for piecewise functions at the x value where you are changing from one piece to another. In order to do that, you first find the limit from the left. This is the x values that are less than that given number, so you're going to use that piece of the piecewise function. You're going to then find the limit from the right, which is the x values that are greater. So you're going to use the piece where it says greater. If the two answers that you get match, then that answer is the limit. If the answers do not match, then the limit does not exist. In example 5b, we are going to put this idea into practice. We want to find the limit as x approaches 0 for the function of f of x, where f of x is a piecewise function defined as 3 minus 4x if x is less than or equal to 0, or x squared plus 2x plus 3 if x is greater than 0. So what we need to do is do the limit from the left and the limit from the right. So the limit as x approaches 0 from the left of this function means that we are looking at the items that are less than 0. That means we are using the top row. So we want to do the limit as x approaches 0 from the left of the function 3 minus 4x. That's just a polynomial function, so we're going to substitute the 0 for the x, and we're going to stop writing limit. So we're going to have 3 minus 4 times 0 is 0, which gives us 3. Now we also need to do the limit from the right. As we approach 0 from the right for this function, that means greater than. So that means we need to do the limit as x approaches 0 from the right for the polynomial x squared plus 2x plus 3. If we substitute into that polynomial, 0 squared is 0, 2 times 0 is 0, plus 3 gives us an answer of 3. So what we have now found is that our two-sided limit, because we approached 3 from the left and from the right, we got the same answer. That means that our two-sided limit is 3. On example 5c, we are doing another piecewise function. This time we are doing the limit as x approaches -2 of the function f of x, where f of x is defined as x squared plus 6 over x if x is less than -2, or 2x squared plus 5x plus 1 if x is greater than or equal to -2. So again, do from the left and from the right. So your limit as x approaches -2 from the left of this function means that you need to use the top row. The limit as x approaches -2 from the left of x squared plus 6 over x. As long as it does not make the denominator equal 0, and since we're approaching -2, we're good, you can go ahead and just substitute the number into the function. So we would get -2 that we are squaring plus 6 over -2. That would give us 4 plus -3, which equals 1. Now do your limit from the right. If we approach -2 from the right for the function f of x, that means that we are using the bottom row. And our bottom row is 2x squared plus 5x plus 1. Putting -2 into this polynomial will give us 2 times -2 that we are squaring, plus 5 times -2 plus 1. Negative 2 squared is 4 times 2 gives me 8, minus 10 plus 1. If we do 8 minus 10, we get negative 2 plus 1 gives us negative 1. So from the left, we got positive 1 on our limit. From the right-handed limit, we got negative 1. Because we got two different answers, what we say about this function approaching negative 2 is that it does not exist. The limits of rational functions will be very similar in that you will just plug in the c wherever you have x's. A rational function is a function that is fractional in form. So you're going to do the same thing. You're going to plug in the c wherever you've had x's. But there are problems because sometimes when you plug in c on a function, you will get a 0. And you cannot have a 0 in the denominator of a fraction. So we are going to look at the idea of what happens when we have a rational function and the different types of things that can result. To find limits on rational functions, you are always first just going to substitute the c in for x and see what happens. There are 3 cases for evaluating limits on rational functions. Case 1, you substitute in and you get a over b, number over number. This is your answer. You are done. One thing you do need to remember is that if you substitute in and you get 0 over b, 0 over some number, that just equals 0 and your limit will equal 0. If you substitute and you get 0 over 0, this tells you automatically that your original function can be simplified, and you need to do that simplifying and then resubstitute to find your limit. If you substitute and you get a over 0 or number over 0, the limit does not exist. There's nothing else you need to do. You are done. You just write DNE. What you do know if you get number over 0 is that the line x equals c is a vertical asymptote for that function. So on our examples for rational functions, our first one we want to do is find the limit as x approaches negative 4 of the rational function x squared plus 2x minus 8 over x plus 4. In looking at this really quickly, I can see that the denominator is going to equal 0. Negative 4 plus 4 is 0. So now I need to check and see what happens in the numerator, because I now know it's either a does not exist or a simplify automatically because my denominator was 0. If you put negative 4 into the numerator, negative 4 squared is 16, minus 8 is going to give us 0. We've got a 0 over 0. So that tells me that I must simplify this function. We're going back to factoring. Remember those days? Anytime you are changing the way the function looks, but you are not evaluating yet, you have to keep writing limit on the front. So we need to factor that numerator. That numerator factors into x plus 4 times x minus 2 over x plus 4. Well, x plus 4 over x plus 4 is 1. So we are now left with the limit as x approaches negative 4 of x minus 2. Well, that's just a polynomial. And on a polynomial, we just substitute. So We will, now remember, we are substituting. We stop writing limit. -4, that's a negative sign, minus 2 gives us -6. So this limit equals -6. On example B, we have the limit as x approaches 1 of the rational function x plus 5 over x minus 4. Always, first thing we're going to do is substitute and see what we get. If we put 1 into this thing, we're going to have 1 plus 5 over 1 minus 4, which gives me 6 over -3. Number over number. That is my answer. So just simplify and you get -2. Notice I did not write limit on the front of this because I was plugging the number in for x. On example C, I can see very quickly on this denominator that I am going to get a 0. So let's check the numerator. -3 squared is 9 minus 9 is 0. We have another 0 over 0. This means we must simplify the function before we can do our limit. Well, if we factor x squared minus 9, you need to recognize that that's the x plus 3, x minus 3, the difference of squares. Hopefully that sounds familiar. Over x plus 3. Well, x plus 3 over x plus 3 equals 1. So we take that out. We now have the limit as x approaches -3 of what's left, which is just the polynomial x minus 3. So because it's a polynomial, we're just going to substitute in -3 minus 3 equals -6. On our last example for rational functions, I look at this and see very quickly I'm going to get a 0 in the denominator. What happens if I put 4 into the numerator? 16 plus 4 gives me 20, and 20 minus 6 gives me 14. I get number over 0. That is undefined. So what I know then is this limit does not exist. There is no more work you have to do. You just write D and E, you are done. Example 7 is an application for limits, and we are being told that the revenue in thousands of dollars from producing X units of a product is given by R of X equals 10X minus 0.002 X squared. Our question says to find the limit as X approaches 100 of the function R of X. So we are being asked to find the limit as x approaches 100 of that function 10x minus 0.002 x squared. But if you look at that function, it is just a polynomial function. And how do we find limits of polynomials? We substitute our value that we are approaching in for x. So because I'm substituting, I stop writing limit. We are going to have 10 times 100 minus 0.002 times 100 squared. This gives us 1,000 minus 20, which equals 980. It's important to note that up here in these parentheses, they are telling you that when you get your answer, it's that answer in thousands. So it's 980 thousands or 980,000. And how do we measure revenue? Dollars.